All right, back from coffee break. So I'm very happy to introduce Mohammad Kohandel. He is from Applied Mathematics at the University of Waterloo, and he's going to be telling us about machine learning modeling approaches to forecast disease progression. All right, thank you very much.
Yeah, thank you, Dominic. Can you hear me okay?
Yes, we can hear you.
Okay, perfect. Thank you for the kind introduction. I regret not being able to attend in person, but I am delighted to join remotely and share some of our work on the application of machine learning, in particular physics-informed neural network and universal pins in cancer research. Sorry, my camera is that way. I'm facing my computer, so that's why. So today I will cover a couple of applications of pins, as I mentioned, in cancer, and then I will discuss uh, what we call universal pin and their application in learning the action of chemotherapy drugs. So most of you must be familiar with physics-informed neural networks, but just to quickly go through it, it integrates physical laws typically expressed as particular differential equations or ordinary differential equations directly into neural networks. It does it by embedding these laws, and then it ensures that predictions not only fit the data, but also satisfy the governing equations of the physical systems. Um, This results in data efficient learning, better generalization to new conditions, and improves interpretability of the neural network. Um, and in particular, pins are useful for solving problems ranging from fluid dynamics, structural mechanics, quantum mechanics, and of course biology, and for us cancer. And it is very useful whenever the data is sparse or incomplete, which happens a lot in biology. So the loss function in pin is defined as the sum of the data loss, which measures the difference between the predicted value and the observed data. For example, could be mean square error, and the physical loss, which measures the residual of the PDE, enforcing that the solution satisfies the physical law. And therefore, this will be kind of a general form of the loss function for the pins, which is if suppose you have some data available that you want to have MSE for the data loss, and then we have some physical law, which is written as a differential equation, and we have the residual for that one as well. Now, to see some of the applications in cancer, one of them was, that we did was, is the application of pins for characterizing brain tumors. This paper was led by my former PhD student, Cameron Meany. He's now in a company called, Simulation Plus, and it was in collaboration with Dr. Doss and Dr. Kolak from St. Michael's Hospital in Toronto, which they provided the patient data to us. So as you know, GBM, or glioblastoma multiforme, is one of the deadliest brain cancer with a survival time of 6 to 12 months post-diagnosis. This project aimed to estimate GBM patient-specific parameters from routine MRI data using mathematical modeling to understand the growth and treatment response. We were provided MRI images of 5 patients taken at 2 different times. So this model, which also called proliferation invasion model, or just it's a simple reaction diffusion equation, is a well-studied mathematical model for brain tumors and represent the density of tumor cells at time t and position x. The model has 3 parameters: diffusion coefficient, proliferation rate, rho, and carrying capacity k. And as you know, the parameter D and rho are crucial for moderate tumor growth, but they're often difficult to measure from imaging data. The standard method to infer these parameters relies on some assumptions. If we assume radial symmetry and exponential growth instead of logistic and constant diffusion, then the PDE will be reduced to a simpler form that can be solved with a straightforward initial condition. And then for large times, the diameter of detectable tumor, assuming that it grows linearly with time, it allows us to obtain the relationship between the velocity and diffusion coefficient. Now, with an estimate for the growth rate and the velocity, we can drive a value for diffusion coefficient. And as I mentioned, this method depends on several approximations, and it's sensitive to noise and relies on human measurements. Here is the proposed pipeline. It includes brain image segmentation using a deep learning algorithm, and then conversion of images to tumor density, and then using PIN to infer unknown parameters in the PDE. We first validated the model on synthetic data and performed sensitivity analysis on synthetic tumors. So basically, we generated some data by ourselves using the mathematical model. We knew what was D and rho, and we wanted to see whether pins can make the prediction. And we added some noise and see how robust is model in predicting these values by adding noise as well. So then we applied this pipeline to patients' data after we tested the network using synthetic data. The cellular density profiles at 2 different points were used as input to the PIN to estimate diffusion coefficient and the proliferation rate. The results are here shown in this table, and seems to be in reasonable biological range that we expected. After getting the parameters, then you can put it back into equations and run simulation and see whether the image that you take from image 1 to image 2 makes sense or not. So in this animation, in the top 2 figures, the color represent the tissue type inside tumor. Purple is edema, blue is necrotic, and green is proliferative. And in bottom 2, the color represent the calculated tumor density. White is the highest and black is the lowest density. The left image is the initial MRI of the patient, and the right image is the final MRI. And there seems to be a good comparison between the two. So in conclusion, we have established this simple pipeline for patient-specific characterization of GBMs, providing accurate estimates of the model parameters and intermediate tumor growth, which can be used for GBM treatment planning. There are, of course, many extensions to this work. One can include, non-constant, diffusion coefficient, like, diffusion matrix, and use, other type of, imaging techniques. We can also add, treatment like radiotherapy or chemotherapy to this, pipeline, and that's what we are working on now. The next project I wanted to do as an example that how these neural networks can be useful when they are combined with mathematical model is regarding the interstitial fluid pressure inside the tumor. This work was also led by my former PhD student Cameron. We know that tumor microenvironment is characterized by 3 key factors. It's low oxygen or hypoxia, acidity, and high interstitial fluid pressure. These factors play important roles in tumor aggression and reduce treatment efficacy and decrease overall survival. And so measuring IFP in vivo is very important, but quite challenging. On the other hand, nanoparticles are used as novel delivery vehicle for anti-cancer agents, and they show preferential, accumulation in tumors due to the enhanced permeability and retention, or EPR effect. Importantly, the accumulation of nanoparticle can be imaged in vivo. So the goal of this project was to use the CT images of liposome accumulations and pins to estimate interstitial fluid pressure and the liposome accumulation over time. This is the key equation which outlines the relationship between liposome concentration and IFP. It describes the change in concentration of a liposome over time, T and space X. LP here is the hydraulic conductivity or permeability of the vessel wall. S is the surface area of the vessel, V is the volume, PV is the vascular pressure, and PI is the interstitial fluid pressure, which is unknown. That's the quantity that we want to obtain. And this is not a constant, this is like it's as a profile, like, as a function of X. The first term in this PDE describes the influx of the substance, from plasma into interstitial space due to the pressure difference between the vascular and interstitial, components. The second term describes convective transport of the liposomes within the interstitial space due to the pressure gradient. And given the size of these, substances, these, liposome, the diffusion terms have been ignored, and they are mainly, through convection. And the last term represents the loss of the substance, due to the degradation or clearance mechanism inside the tissue. So again, we applied the method on synthetic data first. We generated data from the PDE and, knowing the pressure profile. I didn't write the equation for pressure, but we can also get an equation, the PDE for pressure. You can use that to find the pressure profile, substitute into the PDE, and then solve for liposome concentration. And then using the result in the PIN, we compare the predict value with, actual values to access, the model performance. We also perform, sensitivity analysis to synthetic tumors to validate, the model. And we got quite a good comparison between between the synthetic data and the PIN prediction. Again, this is the pipeline for predicting IFP and the spatial and temporal distribution of the liposome within the tumor. All animal experiments were done by our collaborator, Sean, a few years ago during his PhD study at PMH in Toronto, Princess Margaret Hospital. He generated CT images, data set of mouse xenograft tumors, and the interstitial fluid pressure was measured during a modified, Viking needle technique post-injection of liposomes. And these measurements were used to validate the model prediction. So the good thing about the data was that not only we had the CT images, but also we had the pressure at certain point inside the tumor, so we could validate our model. Again, we applied that PINS, PINS uses special liposome concentration maps at the final time to predict a special concentration at earlier times and the underlying IFP. From these special concentrations, we can calculate the bulk accumulation of liposomes, providing values inside. Providing that it provides insight into drug delivery efficacy. One thing that you want to note here is that was kind of an oversimplification, is that we assume that all parameters in the model are assumed to be fixed across different experiments, and we only are obtaining the pressure profile. And that's why we see discrepancies between experimental data sometimes and the animal experiment. What we are doing now is that we are now using additional experimental and animal studies data to find other parameters, and so we can get a better comparison with the actual data. But even though that there was some, disagreement in some cases, not all the cases, we had the data were enough so that we could get, a reasonable agreement with the major interstitial fluid pressure. So the left side, the red ones um, are the measured values for IFP, and the right side, the black dots, are from the model for different mice, and the results are kind of, reasonable. We also have shown that, using imaging data at different time points allows the model to predict consistent values of IFP. So if we pick up any 2 points measurements, we kind of, get a very, very nice, and consistent, result for IFP, which shows, the robustness of the model in capturing IFP and its reliability for, clinical applications. So the conclusion of this work was that, it's this, established pipeline for predicting liposome concentration on IFP using the actual image data seems to be promising. The model have been applied to synthetic tumor and animal studies, and our approach is particularly useful when you want to apply this, for patients, because, many times these, liposome can be used for patients as well, and then we can use the images obtained from the patients to get IFP. And using similar techniques, we can also get information about the hypoxia or any other, biomarkers that we are interested to know about them. So there are many directions that in our group that, we are working on this project. The next thing I wanted to talk about is that, is about, this universal pins, which was led by, my PhD student, Lena Podine, and my former PhD student, Brian Eastman, who is now in OpenAI. The idea here is that the main motivation behind this work was to explore whether we can uncover the hidden structure of models and differential equation using machine learning techniques. There are similar ideas, in the literature, such as neural ODEs and universal DEs, which allow the fitting of functions or entire components of differential equations. As you may know, neural ODEs replace the traditional discrete layers of a neural network with a continuous transformation described by an ODE, and UDE integrates neural network directly into differential equation models. And they allow parts of the differential equation to be learned from data, while other parts can remain as known. In this example of Lotka-Volterra model, U1 and U2 are assumed to be unknown, and the UDE gives the solution of X and Y as well as U1 and U2. So the idea here is that if by any reason we don't know parts of the differential equation, some parts of the physical law or differential equations are known, can we use the experimental data to identify that, unknown component? Working with UDE, we observed that it is quite sensitive to noise in data, as shown in the figure. And even though solutions are reasonable, the hidden terms are not accurately, learned during the using UDE. And since biological data and clinical data is often sparse and noisy, it seems to be essential to address this problem to ensure robust, model performance. And what we have shown that is that, by modifying the standard pin, you can identify hidden terms from noisy data and achieve better, solutions than those of a UDE. And it has, significant robustness. And as can be seen in this, bottom figure, it performs better on, the same data set. I will come back to this figure later, but if you know about AI Feynman or symbolic GPT, these are techniques that we can use so that given some data, you can find the relationship between the variables. So we can use them to find a symbolic form for the given data set, and this way helps in discovering the relationship between the quantities and using the experimental data. So combining the UPINs and Feynman AI or symbolic GPT give us the actual form of the differential equation. So how does UPIN work? In traditional, PIN approach, we assume that the data from differential equation, and the model, the complete model is known. So some parts of the differential, some parameters may be unknown. But in UPINs, model unknown terms with one or more neural network. We model them with one or more neural networks, and we can also enforce conditions with the third loss term. So the way it works is that here is the form of the loss function for UPIN. Include the data loss and the boundary loss and a pin loss. This comprehensive loss function ensures accurate fitting of both known and hidden terms in differential equation, and enhance the model's overall accuracy and robustness. Here, both boundary condition and differential equation can have known and unknown components called B and F here, and B and F here are neural networks. So basically, the known part of the differential equation are given, and the unknown components are replaced by neural networks themselves. So here is the Lotka-Volterra equation that I mentioned earlier, which shows the interaction between this prey and predator populations. And our goal is to apply both UD and UPIN and compare them in identifying these two terms, F1 and F2. So we generated this synthetic data again, and we added noise and sparsity to them. I have already shown this slide on the performance of UDE for the Lotka-Volterra equation, and it highlights the accuracy and challenge faced by UDE in capturing the dynamic system. The top row represent the solution, and the bottom row represent the hidden terms. We tried the method on the sparse and noisy data, and it didn't work well for noisy data, but it did okay on the sparse, noiseless data. And here is the result of the UPIN's performance on the same model and with the same data. And as you can see, UPINs can improve accuracy and robustness, especially in the presence of noise and sparse data. We have also used AI Feynman to identify the coefficients of the hidden terms from data, and the results are presented for both noiseless data with different spacing and fixed spacing and different level of noise. A dash indicate here that AI Feynman didn't recover the functional form, and this showed that we are able to recover the coefficient fairly well for a lot of cases compared to UDE. So in conclusion, here we show that UPIN approach effectively recovers the functional form of hidden term with a differential operator using a sparse measurements of noisy data. Now, as an application, I'm just checking my time. I have time, I guess. As an application, I want to now use the same method that I mentioned, this UPINs, for learning chemotherapy drug action. Again, this work was led by my PhD student, Lena Udina, and was in collaboration with my colleague, Dr. Qudsi. So let's start with a simple model to validate approach. We always start with a simple model using synthetic data to make sure that everything looks okay, and then we apply to actual experimental data. So here CT is the concentration of the drug, and NT is the normalized cell count, taking values between 0 and 1. The first term describes the growth, and the second term is the drug-induced cell death. Generally, we assume no information about the drug action of the chemotherapy G. However, for testing purposes, we choose G to have one of these commonly used forms, log-kill, Norton-Simon, and Emax model. Just like three simple models just to generate synthetic data and compare the model. So the key question here is, can we identify the type of drug action from the cell count and drug concentration over time? So we use the set of ODEs to generate synthetic data for T, N, and C with an appropriate initial condition. The proliferation rate by itself can be estimated by applying a regular pin to pre-treatment data. And then we set up 3 neural networks. First, we approximate CT with a network with 1 input T and 1 output C of T. Second, we approximate GTN with another neural network with 2 inputs T and N and 1 output. And then finally, we can get CN by dividing it to CN, and then we have a neural network with 1 input T and 1 output N, which approximate the solution N of T. So here are some of the results for 3 different cases of Luckey, Norton-Simon, and Emacs models. The results show the effectiveness of our approach in such ideal scenarios, and we have successfully identified the drug actions using synthetic data for each model, and it achieves low mean square error for each case. These are also results for identified drug actions from noisy data. So we add some noise, and it again highlights the robustness of model in handling data variability. And despite the added noise, still the approach was able to maintain accuracy in predicting drug actions. This table summarizes the mean square error of recovered drug actions for each model under different conditions, and we estimated the proliferation rate for untreated data using a standard pin, and then fit the drug action using these, estimates. The method shows, as I said, robust performance even with the sparse and noisy data across, all these, various scenarios. So that the model is tested, we consider a modified logistic model, and the reason we picked up this particular model is that, the experimental data that we were using was before, fitted to a similar model. So here, with the proliferation rate and carrying capacity depends on the chemotherapy drug, and pins can be used to fit separate parameters for each dose, but this can be, time consuming, but U-pins can easily, incorporate, between these, dosages, making the process more efficient. So again, for this model, we generated data for 3 drug dosage with different levels of noise. And as shown in the figure, the proliferation rate and carrying capacity are decreased by increasing the dose. The results here show that predictions are interpolated well between data points. And it seems that U-pin can provide an alternative way to fitting multiple pins for individual data points, with added capability of interpolating between the observations. Next, again, we aim to learn the doxorubicin dynamics from in vitro data set this time. So we start with patient data, first example. Second example was in vivo, animal experiments, and the last one is in vitro data. The experiments were gathered and modeled by McKenna et al. This is Thomas Yankelov group at Texas, and were kindly shared with us. So specifically, here we aim to learn the time-dependent net proliferation rate of doxorubicin for different dosage using experimental in vitro data. The authors collected time series data on cell growth over time. Doxorubicin was applied to cells for 6, 12, and 24 hours at 9 different concentrations. And after the drug was removed, the cells were allowed to grow undisturbed. In the paper, these data was used to model the dynamics of drug. This is the model that they developed for doxorubicin treatment. The OD models, the time-dependent death rate KD in 2 different ways: equation 5A and 5B. They fit parameters using these 2 forms of KD, and they use a weighted combination of 2 models for the final prediction. So some of them are treated with KA and then KB, and then they did this weighted combination. So the question is, can we use U-pin to learn time-dependent term KD within the OD directly from in vitro data without making any pre-existing assumption. So if the true underlying equation is not known, the net proliferation can be learned from the data directly. As you know, we have simplified the form into two cases. The first one is that we replace all details by FDN, and then for each dosage, replace F with a neural network and obtain a function of the number of cells and time t. Second, if we know that the growth is logistic, then we can adjust it accordingly. And then for each dose, replace G with a neural network as a function of time. So the idea here is that, you know, as many information as you have and you're confident with, you can include, and the rest of them you can assume to be unknown and replace it with the neural network. So this is the first model that, you know, we have replaced these two parts with just a function FD, assuming that we don't have any information about them. And this is the second model, assuming the logistic growth is known, but the rest of them are assumed to be unknown. We normalize the data to range 0 to 1 for each dosage, effectively setting theta D to be 1 in each case. The reason is that because of theta D was replaced by a second neural network, the two functions would no longer be identifiable given a data set. Due to the absence of ground truth net proliferation rate for in vitro experiment data, we again, you know, validate the method using simulated data first. For our in silico analysis, we generated time series data for the number of tumor cells over time using realistic parameter values. Parameters were chosen based on fitting result by, you know, McKenna et al. And noise was added to the synthetic data for, you know, noise robustness. And the data for each dose was normalized so that both time and cell count range from 0 to 1. The plot shows the fit of FD to data as well as OD solution generated using the inferred, you know, FD, along with the generated data for the comparison. FD is recovered well using UPIN method, and the resulting model using the recovered FD matches the data well, shows really a good, you know, comparison between the data and prediction, even by adding, you know, a lot of noise to the system. Similarly, we obtain, you know, good results with model B, where, you know, we assume that it's logistic growth, but we don't know the rest of the components of the ODE. We then fit, you know, synthetic data from equation 5b using GD and assume logistic growth. And again, the results are, you know, reasonable, except, you know, GD is not identifiable for large T. This is because the function shown is very flat up until T equal to 0.4, but the derivative increases after that point. And finally, this is the result for the actual in vitro data. Now that the model has been validated using the synthetic data, we then apply to in vitro data, where we only have shown the learned function and the total number of cells for, you know, for one of the concentration of, you know, doxorubicin, which is 312 nanomolar, and an exposure time of 6 hours. This curve is, you know, as you can notice, you know, is very similar to the shape that, you know, was shown in the previous figure. The peak occurs at approximately the same height as well. There is no ground truth for the learned function on the left, so we only make, you know, qualitative comparison here. These are also the results for the time-dependent net proliferation GD learned for the same, you know, in vitro data set. It's important to notice that this curve is not possible to conduct using the mathematical model, you know, in their paper A and B, or, you know, alone or in combination, or even with, you know, a weighted average of this model. So it's quite, you know, impressive that, you know, the neural network could capture all the properties, together. In conclusion, UPIN can be applied not only to cancer or quantitative system pharmacology in any physical system that we have with unknown components and some experimental data, either noisy or even noisy or sparse. We can apply the method to identify the unknown components of the differential equation, and hopefully this helps for physical discovery. And for us, when we don't know the action of a drug or we don't know part of the pathway, we can use the method and the experimental data to determine those unknown components. So I'm going to stop here with my acknowledgement for my PhD student, Bryden Eastman, Cameron Meany, and Lena Podine, and my collaborators, and acknowledgement of financial support from NSERC and CIHR, which are main agencies in Canada. Thank you so much.
Thank you so much for this interview.